welcome to the third portion of Chapter 8, Types of Chemical Reactions. For today, we're going to be learning to use the Regents reference table to predict solubility of ionic compounds. We're going to learn to write a dissociation equation, and later on today also we'll be able to predict the products of double replacement reaction. And later, we're going to examine how to write chemical equations, both net ionic and ionic equations for double replacement reactions. Our focus today is going to be on these three learning targets: reference table, dissociation reactions, and being able to predict the products. So what happens when I put a salt into water, say sodium chloride? In this particular case, when we refer to a salt, we're not referring to what we know as sodium chloride or table salt. What I'm referring to is any ionic compound. So what happens if I dissolve any ionic compound into water? Well, here we're taking sodium chloride and we're placing it into water. We know that the sodium chloride dissolves in the water. So what does that mean is actually happening? What's actually happening is that the ions are breaking away from the crystals, as we can see here in the picture in the larger circle. The ions are actually separating, the chloride ions are separating from the sodium ions, and they end up very farly spaced out where water is in between. So what do we refer to as dissociation? Dissociation is a process where separation of an extended lattice of ionic compounds, the ionic compounds spread out in solution. Okay, this usually occurs in ionic compounds only. It does not necessarily occur in covalent compounds, and there's a very different behavior for covalent compounds. So what is actually happening, as we can see here by this animation, is here's my sodium chloride crystal structure. The ions begin to separate, as we see here. Here's the chloride ion, here's the sodium ion, and in between the water molecules separate. Now, remember that water is a polar molecule that has a fairly large dipole moment towards oxygen, resulting in a partial positive on the hydrogen side, shown here in white, and the negative on the oxygen side. Now that's very important for water's behavior when water interacts with, say, an ionic compound. So what happens is the water molecule can stabilize or interact with favorably a negative ion here, shown with chlorine, by turning the positive end of the water molecule and facing the negatively charged ion, or at the same time it can also turn the water molecule the other way, where the negative charge is facing the positive charge, the positively charged sodium atom. So water has a very unique behavior in that way, that it can interact with both positive and negative ions. So when an ionic compound is dissolved in water, we've already seen from lab that it's able to conduct electricity. Why is it able to conduct electricity? Is because there are free floating ions in solution, and they're surrounded by water molecules. So when we remove all of the water by evaporation or distillation, we can recover the sodium salt that remains behind. So how do we show a dissociation reaction on paper? Because it doesn't seem like there's no chemical change that's occurring here. So how would I show this on paper? Because remember, this is just simply a physical change. The ions are simply being separated, and new water molecules are interspersing between the ions that were previously there. So here's sodium chloride solid mixing with water. Now there's a couple of different ways that we could represent this equation. Here I'm choosing to represent this where water is over the arrow. Water can also be in the reactant side and placed next to sodium chloride, as it would be here. I would just have a plus H2O in front of sodium chloride, or even after it. So what happens here is that the ions separate. So what does that mean? So what that means is the sodium ion separates from the chlorine ion, and they're now both aqueous. The positively charged sodium ion and the negatively charged chloride ion are aqueous. They have separated into their component ions. Now keep in mind that these are the component ions in an ionic compound. So we're getting sodium and chlorine. Now take a look one more time to see that there's only one sodium atom here inside the compound, and one chloride atom here. ion, excuse me. So now our product is a sodium plus cation and a chloride minus anion in aqueous solution. So pause the video here for a minute and attempt to predict the product for the following reactions. So let's look at the product and the process for the first reaction, magnesium chloride dissolving in water. Here, this is a little different because now, as different from the first example, there's no subscript in sodium chloride. Here in magnesium chloride, there is a subscript, and that subscript in the chemical formula tells us that there are two ions of chlorine, two chlorine anions more specifically, in every compound of magnesium chloride. So that means that two ions of chlorine are going to be, two anions of chlorine are going to be lost, and one anion of magnesium is going to be lost or separated when this compound is placed in water. So let's take a look at what happens. So what happens is we end up with magnesium, which has a 2+ charge. We know that from the reference table going magnesium is in group 2, and group 2 elements generally will take a +2 charge. Chlorine ions, on the other hand, will have an anion version, and they take a -1 charge because they are one group away from group 18, so they will tend to accept 1 electron. But what's unique here is now there is this coefficient that is necessary in front of the chloride ion. Why? Because at the start, we had 2 chloride ions to start with in the ionic compound. So therefore, in our product, there must be 2 chloride ions also. So while on the left side, this 2 represents the chemical formula, meaning that there are 2 chlorine ions inside this ionic compound. On the right side, when there's dissociation, we can no longer write the subscript 2. So now instead, that subscript 2 becomes a coefficient 2 to ensure that the equation is balanced. So let's look at the second example. Here's ammonium sulfate dissolving in water. Again, here we have the ammonium ion and the sulfate ion that make up the ionic compound. Now keep in mind that these are both polyatomic ions. So being that they're both polyatomic ions, they will not separate into their individual components, but they will separate as polyatomic ions, looking like this, where it separates into the ammonium ion, 2 of the ammonium ion, because there's a subscript 2 next to the ammonium on the left side, and 1 sulfate anion, as there is no subscript next to the sulfate ion on the left side. So that gives us 2 ammonium ions and 1 sulfate ion for the dissociation process here. So what happens with covalent bonds? So I've already said before that generally covalent bonds don't dissociate in aqueous solution. So what does happen, and how do we write that dissociation process? So here is sugar. This is the sugar that you will mix your tea with. This is the sugar that you add into drinks and other things. So it's in a crystalline form shown here in my diagram, shown by the white crystals. And then the water molecules are surrounding. So in the same way that with sodium chloride previously, there was a separation of the ions, here we have not a separation of the ions, but separation of whole molecules of sugar. Sugar does not dissociate into individual components, individual ions. Sugar is a covalent compound. Its general formula here is C12H22O2 dissolving in water. And what do we get? We end up with C12H22O2 without any charge. And simply to distinguish when it's dissolved in water and when it's a solid, when it is a solid, we place AQ next to the compound in the chemical dissociation process. So here there is no dissociation for covalent compounds, particularly sugar in this particular case. So we also know that not all dissociations are going to be equal, because not all ionic compounds are equally soluble. Okay? That is, any ionic salt, any ionic compound will not necessarily dissolve. How do we know which ones will dissolve and which ones won't dissolve? Well, there is a very quick way to do this. we can look at table F in our Regents reference table. Now this table is slightly confusing the way that it's been written, because while it says the solubility guidelines for aqueous solutions, in fact this is not one table. It is in fact two separate and unique tables. On the left, it shows ions that form soluble compounds. So in the table on the left, this shows solubility rules. In the table on the right, this shows you which compounds are insoluble. So we can take a look at this table and recognize that all group 1 elements are soluble. All ammonium compounds are soluble. All compounds with nitrate are soluble. All compounds with acetate and hydrogen carbonate and chlorate are soluble. Now all halogens are soluble except for silver, lead, and mercury too. Okay? Those are the exceptions to the rule. So that means these three salts with chloride, bromide, or iodide are insoluble. In the case of the sulfate also, so all sulfates are soluble except for silver, calcium, strontium, barium, and lead. So that means these 5 salts, silver sulfate, calcium sulfate, strontium sulfate, barium sulfate, and lead sulfate will form insoluble compounds. And on the other side, we can see that really these are just very few exceptions that we have here. All carbonates are insoluble except when interacting with group 1 and ammonium. But if we go back, remember that all ammonium compounds are soluble. There are no exceptions. Right? There are no exceptions for ammonium, and there are no exceptions for the group 1. That means all group 1 and ammonium salts are soluble. If we go down and continue, we can see that chromate, phosphate, sulfide, all of them are mostly insoluble except for a few cases. Now, the cases over here are the exceptions, meaning that these show soluble salts. So please remember that when you are reading this table, that the table on the left shows the solubility rules, while the table on the right shows the insolubility rules. So let's stop here for a second and take a moment. You can pause the video here and try to predict the solubility of the following 3 compounds. So if we take a look at the top compound, this is copper 2 sulfate, it's given as a name. So the first thing that we may want to do is we may want to convert this name into a chemical formula. So we can take that name and convert it into a chemical formula. We get copper. We would have copper 2, Cu, 2 plus, and then SO4 would be our cation, would be our anion. So it would be a 1-to-1 ratio, and here it is. And if we go to your Regents reference table, you will see that this is a soluble compound, copper sulfate. And we've also worked with copper sulfate in the lab on a number of occasions. It forms a very pretty blue-colored solution. Let's take a look at lead nitrate, lead 3 nitrate in this particular case. So if you remember from the table, all nitrates are soluble. Therefore, this is a soluble compound. Taking a look at the last one, this is zinc hydroxide. Zinc hydroxide is part of the hydroxide family, which is an insoluble compound, so we'd use the table on the right. And if you look at the table on the right, we would discover that all hydroxides are insoluble for zinc, except for just a small number of hydroxide compounds. And zinc does not fall into that category.